All right, your next assignment is due a week from today. And as a reminder, the class for 2 days from now, Thursday's class is posted online. We've talked about that from the beginning of the semester. That's a planned meeting that I've known about for a while. Here's the notes for that, and I've already sent you the link. And I haven't actually checked to see if anybody watched that one over the weekend, but it's a really important lecture that the entirety of the homework assignment, all 2 problems of it, is covered in this recorded lecture that's posted online for Thursday. And you'll notice that the assignment is due before we have a chance to meet in person again. But I think that's okay because I do a demonstration in that recording that is very detailed, and if you just do the same thing that you saw in the screen recording, then you'll be in fine shape for the homework assignment. I think the recording for Thursday is a good one. Good enough that it's okay for us to have that assignment due next Tuesday in class. Of course, I will be in the office next Monday. I don't have office hours on Mondays, but next Monday, the day before this assignment's due, I'll be in the office except for a 1-hour meeting that we have with President Kopp. Besides that, I'll be there, I think, most of the day. So schedule-wise, does anybody have any questions about what's going on in the coming class periods? Everybody's got both sets of notes. Okay, well, today we're going to be talking about non-circular conduits. What happens when the pipe doesn't have a diameter? How do you make substitutions into the equations where it's always talking about D? And then we're also going to look at a problem, a couple of instances where local losses are important. So here are just a couple of pictures of situations in the real world where water would be flowing through a non-circular conduit. The image on the left are pipe culverts in the UAE. When I lived over near Dubai, there were these roads out in the middle of nowhere, roads in the desert that would have these enormous pipe culverts. I have another picture where I'm standing underneath it, and I'm only about half the height of that pipe culvert. It's very big, and there's 2 of them. And the reason why, as I told you earlier in the class, they have these flash floods that come through, and not very much water is going to infiltrate into such rocky, impervious soil, and so when it rains, the water just rushes through there very quickly, and they have to have generously sized culverts to accommodate all the flow. But trying to calculate how much water can get through this culvert is a little bit of a challenge because of the geometry of it. So not every conduit is circular and has the hydraulic radius just D divided by 4. Sometimes it's more complicated than all that. Occasionally there will be square pipes with water flowing through it, usually in very tight quarters where they're trying to maximize the flow area and minimize the width. Would it be a rectangular conduit? So in instances like this, we can't substitute diameter into the flow equations. And by the way, I have to just pause for a moment. I forgot to introduce our visitors. There's so much going on. I'd like to introduce Jin Kim and her daughter Yoo-Jin, and they're both visiting from Korea. They're just taking a tour around Marshall University today, and I'm very happy to have them here. And they picked hydraulic engineering as the class to sit in on because, obvious reasons, it's the most interesting class on campus, and so we're very excited to have them here today. Sorry I didn't introduce them earlier. Okay, back to non-circular conduits. So we have to make some adjustments to the flow equations for that. In order to calculate the hydraulic radius, by definition that's the area divided by the wetted perimeter. And when it's a pipe that's flowing full, we can simplify the hydraulic radius just to be the diameter divided by 4. That's not the case if the pipe isn't entirely full. If the pipe is only partially full, it actually is very challenging for us to calculate both the area and the wetted perimeter. We don't get into the geometry of a partially flowing full pipe until towards the end of the semester. Frankly, it's kind of a nightmare a little bit. But the Darcy-Weisbach equation, when we have a non-circular conduit, you'll notice that we have 4 times the hydraulic radius substituted in where diameter would ordinarily be. So 4 times r sub h is what we exchange for the diameter. It's an equivalent diameter. If the pipe were made to be circular, then 4 times the hydraulic radius gives you that equivalent diameter that you can substitute into the Darcy-Weisbach equation. So we make that same adjustment for the Reynolds number, which ordinarily would have the density times the velocity times the diameter divided by the viscosity. And so that substitution of just 4 times the hydraulic radius works again. We've got kinematic viscosity is the absolute viscosity divided by the density. And so this one is 1 times 10 to the minus third, and if we divide it by 1,000, that's where 1 times 10 to the minus sixth comes from. So this is where you've got absolute viscosity and the density together. Yeah? Yeah, yeah, it is. The cross-sectional area in the case of, the pipe would just be whatever length and width you've got, or in the case of in a regular cross-section like this, you'd maybe need to make an estimate based on the shape. Usually on an elliptical pipe culvert like this, you can get many of the geometric parameters directly from the manufacturer. They'll tell you what the cross-sectional area is, and sometimes even the wetted perimeter for certain depths.
Those pipes like that will flow.
Yeah. They actually, the clue that they think it's going to flow full, you can't see it, but they've got chain link up against the gravel here. They're fully prepared for the water to actually go over the top of the road there. Yeah. And so it's at a pretty shallow angle, and they've got big cobbles there with chain link over it so that when the water comes flowing down through the wadi, as they call it. Now out west they have canyons. Here in West Virginia we have hollers. There they've got wadis, they're called. And in fact the water park there is called Wild Wadi. So the idea being like the water slide is like you're going down one of these wadis. But yeah, so they've got chain link all the way against the face of that to try and keep everything in place. Well, if the water came rushing towards that, it could erode it if it was just soil, or if the rocks weren't held into place. It's just a way for them to sort of keep the rocks that are up against the face of that in place when the water is coming through. Yeah, out in the middle of the desert. Okay, so let's take a look at an example just so we can get a feel for doing the calculations when we have a non-circular pipe. We have a rectangular box culvert here, 12 meters long, and we know the equivalent sand roughness for this concrete box culvert is 1.6 millimeters. We know the width and the height of the box, and then the flow rate is 0.4 cubic meters per second. So if we assume that it's flowing full, we want to find the head loss according to the Darcy-Weisbach equation here. We're just going to make the substitutions for the hydraulic radius being put in place where ordinarily we do the diameter, and doing the same thing here, you'll notice that instead of diameter we have 4 times the hydraulic radius in the Jane equation as well. So for a non-circular pipe, length is 12 meters, case of best 1.6 millimeters. For which equation? What's the Colbert equation? Oh, Colbrook equation. I thought you were saying culvert equation, because we were just looking at a picture of a culvert. I was still in culvert mode. Yes. Yeah. Yes, that's right. Yeah. Yeah. Okay, so for a second there you were getting worried when I said, what's the Colbrook equation, right? Yeah. No. I remember what the Colbrook equation is. All right. For the cross-sectional area, the wetted perimeter for this, if we have it being 1.25 meters on each side then the wetted perimeter is just going to be 4 times each of those sides. So 4 times 1.25 meters. 5 meters is the wetted perimeter. And so we can calculate the hydraulic radius is going to be the area divided by the wetted perimeter. And that gives us 0.3125 meters as the hydraulic radius. Okay. Since it's flowing full, it's easy for us to calculate what the velocity is going to be. Velocity is just the flow rate by the cross-sectional area. Okay, and it's 0.4 cubic meters per second divided by 1.5625 meters squared. And that gives us a velocity of 0.256 meters per second. Okay. Now that we know that, we can find the Reynolds number with the density, velocity, 4 times the hydraulic radius, and the absolute viscosity. 1,000 kilograms per cubic meter. The velocity is 0.256 meters per second, and 4 times 0.3125 meters divided by our absolute viscosity was 1 times 10 to the minus 3 Newton seconds per meter squared. Like, why am I not just doing, why didn't I just say, there's no particular reason. Yeah, I could have done that. Well, remember that when we said that the pipe is flowing full, we said that, all right, the hydraulic radius is area divided by wetted perimeter. And if it is a pipe that's flowing full with a certain diameter, then what we'd say is it's pi d squared divided by 4. And then the wetted perimeter is just going to be pi d, because that's the circumference around there. And so if this is a pipe that's flowing full, then the hydraulic radius is d divided by 4, because we can cancel out the pi, we can cancel out this d and one of the ones in the numerator, so it's just d divided by 4. So if we say diameter is really 4 times the hydraulic radius. So anything that's flowing full is going to have this relationship. And so if it doesn't have a diameter, if it's some other shape, then instead of putting in the diameter, we can say 4 times the hydraulic radius, regardless of what that shape is. That's why it works out for us to make that substitution. Now, if it's a really bizarre shape, you know, like if it was a rectangular conduit and this is the pipe, probably edge effects are going to throw things off, where you couldn't make the substitution of 4 times the hydraulic radius with this shape, even if it had like the equivalent area of another pipe. You know, there are extremes at which this substitution won't work out, but for anything reasonable, like we're doing in this example, it'll work just fine. Does that answer your question? Yes. All right. So the Reynolds number works out to be 320,000. And Reynolds number is unitless. Tells us we are definitely in the turbulent zone, not even close to laminar. So instead of that Reynolds number divided by 64, which is what we could do to find the F value if it was laminar, we'll use the Jane equation. Okay. 1.325 divided by the logarithm of K sub s is 1.6 millimeters here. And we're going to have that divided by 4 times the 312.5 millimeters. Now, earlier I found that the hydraulic radius was 0.3125 meters. Since I know the equivalent sand roughness K sub s in units of millimeters, I want to make sure that I either convert that to meters and then use hydraulic radius in meters, or convert the hydraulic radius to millimeters, because it has to be dimensionally consistent. I went with changing the hydraulic radius into millimeters. Okay, and then times 3.7 plus 5.74 divided by the Reynolds number, 320,000 to the 0.9 power. Not at all. It would affect the final answer if I'd left this in millimeters and I had that in meters. But if I convert that to meters and then have that in meters, it's going to be the same. Square it. Okay. So that F value works out to 0.0218. And then finally, we can substitute it into the Darcy-Weisbach equation. H sub F is FLV squared divided by, instead of D, I'll have 4 times the hydraulic radius, 2G. Okay, so that is 0.0218. The length is 12 meters. The velocity was 0.256 meters per second. 4 times the hydraulic radius, 0.3125. Back to meters now, because the length parameter in L was in meters. 2G. Okay, so this is pretty minor head loss here. The water's not moving very fast, and it's a pretty big box culvert, and that's why there isn't much head loss. But it does illustrate what we need to do when we have a non-rectangular, non-circular conduit. Yeah.
H and F and H and F are the same thing, right? That's both.
Just head loss has 2 terms, and that's a good transition to our next topic. Head loss is the friction losses and the local losses. We often either don't have local losses or we ignore them. Here, for example, we're just talking about some length of pipe, and there really isn't going to be like a valve or a pipe bend. And so in this instance, then we'd say there's no local losses, and so the head losses are entirely because of pipe friction. So HL and HF are the same usually, but if you have fittings or valves that are taking a significant amount of head, then they're not equal. HL and HF. HL is composed of HF and H naught.
So when you put it into the energy equation,
Yeah.
you put HL in that, right?
I do. I put in HL to represent the friction losses and the minor losses. The last example we're going to work today has both. So you'll get to see us having to deal with both simultaneously. All right. Speak of the devil, there it is. All right. Local losses are sometimes referred to as minor losses because ordinarily they only account for a small fraction of the head that's being lost from one point to another. The pipe friction is usually dominating the energy losses, but that's not always the case. You'll notice that in order to calculate the local losses, H naught, there will be some K factor. We can look it up off of a table or it will be given, and that's an indicator of how much turbulence is induced by a given fitting. And so whether it's a globe valve or a gate valve, each of these different valve types have a different K value that you can look up. And even from manufacturer to manufacturer, the K value may be slightly different. But you look up the K value, which tells you how much turbulence there is from that fitting, and then multiply it by the velocity head. And the velocity that you use is the velocity as the water goes into the fitting. In most cases, the velocity will be the same inlet to outlet because the diameter into a valve isn't any different from the diameter out of the valve. But if you have a pipe diameter that is changing, you have the flow in with one velocity and the flow out with another velocity. The K value that you'd use is typically calibrated such that it's according to V1 being the K value is based on V1 dominating the amount of energy loss that there is. Sometimes you won't even use the difference. You'll just use the inlet velocity through a change in diameter. What's different about a local loss instead of a frictional losses is that it's just at a single point instead of being distributed over this entire area of a pipe. And it accounts for entrances, meaning when water goes from a tank into a pipe, you lose energy there. Anytime a pipe contracts or expands, and in fact even a channel, we're not just talking about pipes, local losses can apply to channels as well. When a pipe changes diameter, you have turbulence that's induced from that, and when a river changes diameter, that causes a little bit of turbulence in the river. Anytime flow changes direction because of a bend, that's another thing that can induce turbulence, and so can all of the fittings and valves that exist typically in a home. There are a lot of places where a spigot may have a T junction because you want to have a pipe going off to maybe the garage or somewhere out of the house, or you'll have a valve which splits the water into the hot water heater and then a separate cold water line into the house. Each one of those things inside of the house takes a little bit of pressure out of your system, because remember that if the diameter can't change and the elevation is constant, the way a head loss manifests itself is just as a reduction in pressure from the upstream end of the fitting to the downstream end of the fitting.
I guess you could have like a large or a long pipe network. You could have a bunch of exits.
That's right. Yeah, you could have more than one.
Okay.
Yeah. Here's a table from your text, and I just wanted to point out a couple of things, a couple of trends that are interesting and important to observe. The first is that let's consider a contraction. A big K value means there's going to be a lot of energy loss. So you can think that you're always trying to preserve pressure. Just losing pressure due to losses is a pity because pressure is expensive. You've got to lift water to a really high tank to get that pressure, or you're burning up electricity in a pump to generate pressure. And so pressure is this precious resource that you want to preserve so that people can have a blasting shower at home, right? People always complain about too little pressure, but they rarely complain about too much. They can just turn the valve a little bit more closed. So if a big K value is bad, let's look at what causes big K values. These are D to D is the ratio of the downstream diameter to the upstream diameter. And if it's 0, that means that the pipe isn't changing size at all. But 0.2 means that the upstream pipe is only 20% the diameter of the downstream pipe. And so another thing that's a factor that comes into play is the angle here. Is it going to be a gradual transition, like the 60-degree angle would mean that it gradually transitions from the big pipe to the small pipe, versus 180 means it just instantaneously goes from big pipe to little pipe and there's no transition zone. And so if you look at the first line here, this 20%, it's a pretty big pipe going into a pretty small pipe, then you would have a lot more energy loss for the 180-degree transition than for the more gradual transition. You're only going to have 0.08 for the K value versus 0.49. So If you have a more gradual transition, then that helps to avoid some of the turbulence that otherwise would be induced by that fitting. The other thing is the expansion. You can tell that a similar thing applies, that the case where you have a gradual transition versus an abrupt transition, you're going to have more energy loss for the abrupt transition than if it's gradual. The other thing to look at is that different types of valves have different energy losses. A globe valve is 10, which you're losing really a lot of energy through a globe valve than through a gate valve, 0.2. That's very minimal energy loss there. We'll look at some cross sections of what these fittings look like in just a minute. I'm sure everybody heard about the water thing that they had in Charleston, the chemical emergency. I already have a water filter at my house that removes organic chemicals from the drinking water. It's a carbon block filter, but I'm going to be installing another filter because I am kind of pessimistic that this sort of thing's never going to happen again. I think it's definitely going to happen again, and next time it might not smell like licorice, so nobody would notice, you know. So I'm going to put another filter on my whole house, and so I'm designing how I'm going to cut into the existing pipes, and it's sort of fortuitous because I was thinking, oh, should I get a globe valve or a gate valve? And this tells me that if I get a globe valve, I might have a pretty significant loss of pressure. Even when it's fully open, I'm going to lose 10 times the velocity head, and that could be a significant amount of pressure, versus a gate valve that's wide open. You're not losing hardly any pressure at all through a gate valve. So I'm going to have that water filter sort of bypass the main water line and then tie in again, and I'm going to use gate valves because I want to preserve as much pressure as possible.
But I guess if you were to, I mean, just generally speaking, if you use a globe valve and it reduce the pressure down to where it's not going to become, how you put a pump in or something like that.
I could put in a pump. I'd rather not, but yeah, you can always add additional pressure that's being lost. Let's take a look at what some of these look like. One other thing to mention is that in an elbow, how much energy loss there is in a pipe elbow depends on the radius of the pipe relative to the radius of the bend. Here it's expressed the diameter of the pipe relative to the radius of the bend. So let's say that we have a pipe that's changing directions like this. And so if the pipe's changing directions like this, then the radius of this bend, we could say this is the radius of the bend. So it would have some r. And the diameter of the pipe, d, we'll know. And so if you have the radius of the bend relative to the diameter of the pipe of 1, then you're going to have a big K value, 0.35. So you're going to lose 0.35 times the velocity head. That's how much energy is going to be lost through that bend. Now, 2 means that it's a more gradual turn. So 2 would be maybe like that. And why is it that we have a lower K value if it's a more gradual bend? I also drew it as a bigger pipe. Let me try and do better. The same diameter pipe, but a more gradual bend. Why is the K value smaller? It's all about the turbulence that this fitting is causing. And if you can sort of gradually and smoothly change the direction of flow, then you'll have less energy loss. But then it starts creeping up again. 0.17, and now it's increasing. 6, 10, 16, that means you're having a really gradual transition, you'd think that's not causing hardly any turbulence at all if you're changing direction that gradually. So why do you suppose that the K value is increasing again? Because it's longer. It's actually friction losses in disguise. So it's the pipe length and a little bit of turbulence that is factored into this K value. Okay, here's what some of these valves look like. A gate valve is a pipe that a gate can go through, and so that when it's open, there's very little to disrupt the flow. I've got a better cross-section of what a globe valve looks like, but in contrast to the gate where water is just coming through without changing direction when it's open, that's the advantage of the gate. That's why the gate valve has such a low K value. A globe valve has a very unusual path. It's going to have to come in, change flow a little bit, change direction here, change direction again, go sideways, and then exit. It's changing direction like 4 times in the flow path just through the fitting. A check valve is something that's often put into place on your sewer line. You only want your sewer going out of the house. You never want it coming back in. Here in Huntington, they have in a lot of neighborhoods, they've got the problem that when it rains, the sewer pipes will be full, and so the sewage will actually start going back into people's basements. And so often they'll put check valves in to prevent that. And a check valve, there's different kinds of check valves, but you can see that the K values may go as high as 70 for a ball check valve that's open. A rotary valve, I've got a cross-section of a rotary valve. It's basically a pipe section that can be put into line or closed off when you don't want flow to go through the rotary valve. I also mentioned pipe inlets and exits, and if you have water going from a reservoir into a pipe and it's just at a 90-degree angle like this, then the entrance loss is 0.5 times the velocity head. But if it's a pipe that extends into the tank rather than being flush with the edge of the pipe of the tank wall, then it's 1 as the K value that you use. And the same thing is true with the smooth pipe change directions, that if you smooth out the edge of an inlet, then you can reduce the K value considerably as well because there's less turbulence.
So like with the globe valve, what would be its
They're good for really high pressure applications. It's water might leak around the edge of the gate, but you can really clamp down with a lot of force on the globe valve. And so I think it depends on maybe an industrial application where you're going to have super high pressure that you'd want to use a globe valve.
Like gas.
Exactly, yeah. Or when any sort of leakage could be really problematic. You know, when the propane's off, you want it off. A drip here or there from a water line isn't so bad, but it could cause an explosion if it was a gas line.
that professor that was trying out for a job?
I may have missed that one. Yeah. Yeah. This figure, I think, is good at showing the circuitous path taken by water going through a globe valve. And the nice thing about this plug is that you can really have a pretty stout assembly here to put a lot of downward force to seat that plug into the valve seat and keep the flow from coming out. By contrast, a ball valve, which I'm sure you've seen, ball valves are pretty common for where people water their lawns. I guess we don't do that in West Virginia, but out in the western United States where people actually have to water their lawns, you'll see plastic ball valves all the time on their water lines just because it's easy to open and close. You know, a globe valve, you maybe would screw it forever to finally get it switched off, but a ball valve, you know, a quarter turn, a half turn, I guess, and it's all the way closed.
So why don't the K valve, I mean, I understand kind of why the K valve is large in the globe valve,
Yeah.
but I mean, on these other two, the check and the rotary, like it's just going straight through, isn't it?
Well, it's going straight through, but they can't always design the check so that it's completely out of the way. And especially because there's no such thing as all the way open with a check valve. You know, there's a spring. The way that it works is there's a spring that's always sort of trying to push itself closed. And so the check valve may only, you know, the spring is pushing it so that maybe it's part way intruding into the flow because it's trying to always push itself closed, and I think it has to do with that.
Ball type has like a ball that's actually floating.
The ball type check valve? Yeah. All right. So here's our example where we're going to be doing two things actually. We haven't used the Hayes and Williams equation much, just sort of taken for granted that it's easy enough to use that we haven't done too much practice. But we're going to use the Hayes and Williams equation to handle the friction losses, because here in this example, water is flowing through a pipe where we know the length of the pipe is 1 kilometer. From location A to location B is 1 kilometer. We know the pressure here at A. The pipe is pressurized to 650 kilopascals, but we want to know up on this hill, 1 kilometer away, where the elevation is 12.5 meters higher at B than at A. Up on that hill, after water goes through a certain length of pipe and then a bend, we know the K value from the bend. We know that there is a globe valve here with a certain K value, another bend. So we've got 3 different local losses. We're going to need to calculate the local losses due to those. Now, since the water is flowing through the pipe at the same velocity at all 3 of those points, we don't have to calculate the minor losses separately. We can actually just add up all of the K's and then multiply the sum of the K values by the velocity head. If it was different velocities at these different locations, then we'd need to handle it separately. Like if we had a small diameter pipe here and then it got big again. If you have different pipe diameters, then you have to find the velocity specific to each one of the fittings. But here, since the velocity is the same because the diameter is the same, we can simply sum the K values. So the K values is how we're going to calculate the local losses. We will estimate the friction losses with the Hayes and Williams equation, and we want to solve for the pressure at B. So I'll turn you loose to work on that with the partner or individually, and after a little bit of time I'll start transcribing the solution onto the board. So we start by calculating the friction losses using the Hayes and Williams equation. One thing I'll point out is that the Hayes and Williams equation, one of the limitations is we're actually only supposed to use it for pipe velocities below 3 meters per second. So I'm a little bit outside of that range since I've got a velocity of 4 meters per second. So what that means is that the Hayes and Williams equation probably wouldn't perform as accurately as it ordinarily would. And that's one reason why I usually just stick with the Darcy-Weisbach, is because then I don't have to worry about being outside of the range. But that said, we can calculate the pipe friction is about 43 meters of energy loss due to the resistance of the pipe acting against the movement of water over that 1 kilometer. The local losses, I can add up all the K values and multiply it by the velocity as the water flows through those fittings, and I get 8.48 meters of local loss. And then in the energy equation, I set my elevation datum equal to the elevation at location A. That's why I canceled out Z1, as I'm saying let's call Z1 equal to 0. The velocity head cancels in both sides of the equation because the flow velocity isn't any different at A than it is at B. And here, just as a reminder, I've got the local loss and the friction losses. That's the H sub L term that typically we see in the energy equation. So making the substitutions there, you can see that the energy comes from the pressure head at A. This is what everything is going to be subtracted against. The only way we've got pressure at B is if there's enough pressure at A to overcome all of the losses. So the pipe friction loss, the local loss, the elevation change, and there still is a little bit of head left over when the water gets to location B, 21.3 kPa. By the way, that wouldn't actually be enough pressure. Usually a typical minimum pressure for a municipal distribution network is about 350 kPa. Even in an emergency situation, it's recommended that the pressure not fall below 140 kPa. That's typically assumed to be the safe amount of pressure that can keep infiltration from coming in. Because if you think about what happens when the water goes off, is someone opens their faucet and you hear that gurgling sound. That gurgling sound is air actually going into the pipe as the water drains backwards. And so when the pressure is really low at the hill, well, what if there was an apartment building that's tall? And it's 21 kPa here, but if you've got a tall apartment building, eventually the pressure is going to be 0. And so what that means is that someone could open up a valve, maybe a clogged toilet or a sink that's into standing water, and there's a situation where backflow can occur. So usually backflow prevention and having a little bit of pressure left over for firefighting is usually what drives that minimum of 140 kPa. We'll talk a lot more about minimum pressures and the risks involved with backflow when we get into the project that we're going to do midway through the semester. That's it for this example. Are there any questions on this one?
Is there a way to convert the C value to a fixed decimal?
I don't know of one. Tables will often...
If you're given a C value and double check your answers,
You could calculate the head loss for both if it's measured. Okay, well let's just review these announcements. We aren't going to see each other for a week, so I want everything to be clear about the homework 3. 2 problems are going to be due on Tuesday. And I would encourage you to watch that recording for Thursday's lecture as soon as possible. Don't save that to Monday night. You'll be sad if you start working the assignment Monday night and get into any problems. And I can tell when people watch too. I'll see how many views there are each day. So I'll show you what that looks like. Remind me to show you the Google Analytics for that video. It'll be interesting to see when people watch this. All right, well, have a great day. I'll see you next Tuesday.